Hey guys, welcome to day 3 of your video lesson notes. We are going today be classifying numbers and talking about what set notations are. A lot of this actually you have learned before, so it might be familiar to you guys. Okay, so it is so important in math to know how to classify numbers, especially when we're working with, maybe we're reading directions, right? And they tell us that our numbers have to be integers. Well, what are integers? How do we know that we're writing the correct types of numbers? Okay, so that's why it's important, right? And also a little bit about what we're going to be doing is talking about number lines and how to shade and all of that good stuff. All right, so let's begin. So the real number system. So first I'm going to write definitions actually as we fill in these boxes. So let's think natural numbers. Okay, so natural numbers are just counting numbers. Okay. So first off, what does that mean? Counting numbers. That's gonna be what we think of, and I'm gonna write this in this box here. So we're gonna start with this little box, natural. We represent that with this capital N, and counting numbers would be kind of those first numbers we learned how to count when we were itty bitty. 1, 2, 3, etc. Okay, so no fractions. Notice I didn't write 0. Okay, 0 is actually not a natural number. Way back in the day when math wasn't even really a thing yet. They didn't have the number 0. Okay, they just said you didn't have anything. Okay, so they wouldn't say, hey, I have 0 sheep. It's just that they didn't have any sheep. Okay, so 0 wasn't even a number that existed at one point. Okay, so these are natural numbers, right? I have 1 sheep. I have 2 sheep. It wouldn't make sense to say I'd have 1.5 sheep. Okay, that would be a little scary. So natural numbers are counting numbers, not 0. Whole numbers, though, now that will include 0 and the counting numbers. Okay, so notice I'm going to write whole. In this box here, we represent whole numbers with a capital W. Okay, and notice that this box that I wrote whole in encompasses natural numbers. So not only does whole numbers include 0, it also includes the numbers in this natural numbers box. So 1, 2, etc. All right, next we have integers. So notice so far I've only been writing either 0 or positive numbers. So integers will include negative numbers as well. So we have 0, and then we will have positive and negative. Counting numbers. Okay, so I'm gonna write my integers in this next box. So notice it encompasses whole and natural numbers. We represent integers with a capital Z. And notice I'm going to write negative numbers as well. And it includes also anything else in these smaller boxes within it. All right, next we have rational numbers. So rational numbers are going to include everything up above plus fractions. So integers, oopsies, integers, keeps doing that. Integers, so meaning everything up above, fractions, and then terminating decimals. And also, I should say, repeating. I'm running out of room here. Repeating decimals, okay? So terminating decimals, that means the decimal terminates, it stops, right? So if we have 0.25, okay, that's also equivalent to 1/4 as a fraction. That's a terminating decimal. It stopped after 5. A repeating decimal, think the fraction 1/3, okay? If you type in 1/3 into your calculator and get the decimal, it's gonna be repeating, right? It's gonna just keep going on forever, ever, and ever, and repeating itself, okay? But repeating is an important component to that. Okay, irrational. So now notice I'm gonna kind of write irrational in a different color because irrational, oops, I forgot, actually back it up. I forgot to write rational up here. So rational will be this big box. We represent it with a capital Q, and it is going to encompass all of the types of numbers in the smaller boxes, but also these fractions and terminating decimals. Okay, so we could have a negative number, 0. We could have 1/2. We could have 0.3 repeating. We could have a negative fraction. Okay, so on and so forth. All right, so back to irrational. So irrational, that would be so notice that irrational, that's gonna go over here in this on the side, meaning it's not going, sorry, that was horrible handwriting. So that means that irrational numbers are not going to encompass any type of number that is in red here on the left-hand side of these boxes. So irrational numbers are non-terminating, meaning they never ever end, but they also don't repeat. So non-terminating, non-repeating decimals. Okay, there's a very famous number, if you can try to think of that real quick. If you've ever heard of pi, that is an example of a non-terminating, non-repeating decimal. It goes on forever and ever, and the numbers don't repeat. They are different. Another famous number we will work with this year is Euler's number. It's an E. We also have certain radicals. So if you type in square root of 2 or square root of 50 into your calculator, you will see that the decimal you get goes on forever and does not repeat. Okay, now let's talk about real numbers. So real numbers, that would be all rational and irrational numbers. Okay, and so real numbers, it's all of these that we've discussed so far. Okay, we will actually, you're probably like, well, what, do we not have real numbers? That we don't. We actually do have numbers that are called imaginary numbers. And they're pretty cool. So we'll work with those a little bit later in the year. But yes, there are numbers that are not considered real. Okay, so we're gonna do some practice. So we're gonna identify which subsets these belong to. I recommend you pause the video, try this out on your own, check all the boxes for each one, and see if you get what I get. All right, but I'm gonna go ahead, hoping that you pause that and tried it yourself. So for 2.3, repeating. So first off, there's a box that we could check for all of these numbers. And what would that be? Well, that is real. Okay, these are all real numbers. All right, so 2.3 repeating decimal. Well, looking back at the rational numbers description, that had the word repeating decimals in it. Okay, so I know that it is rational. Well, if it's rational, it can't, well, because it's a repeating decimal, it's not going to be any of the other types of numbers. Okay, integers cannot have repeating decimals. Whole numbers cannot. Natural numbers cannot. Okay, so we stop at rational. All right, next one, 25. Well, 25, is it rational? Yes, it is. Okay, because remember, rational is pretty much every real number minus the irrational ones. Okay. We also know it is an integer. It is a whole number. It is a natural number. Okay. If it's a natural number, it's also meaning a counting number, right? And 25 is a counting number. That if it's a natural number, then you are able to go ahead and check all the other boxes. Okay, because all of these other boxes, whole, integer, rational, all encompass natural numbers. All right, negative 11 halves. So negative number. So first off, that means we can already eliminate natural and whole numbers because those cannot be negative. Then we also see that it is a fraction. We don't introduce fraction until rational numbers. Okay, so we have here rational. Square root of 5. If you were to put that in your calculator and get the decimal, you would see that it is non-terminating and non-repeating, so it goes on forever and doesn't repeat, so it's irrational. All right, negative 8. Okay, well, we know that it's negative, so first off, it can't be a natural or whole number. Those cannot include negatives, but since it is a negative 8, it's not a fraction, that is an integer. And if we check integer, then we can check off whatever's to the left. And so rational as well. All right, and then pi, well, I kind of gave that away earlier. That is probably the most famous irrational number we have. All right. So let's talk about set notations now that we've classified our numbers. So let's consider the set of all real numbers between 3 and 5. How would we represent this set using a number line? Okay, so first of all, we need to pick out important words. I know a lot of times in math, we don't think that, the words or directions or what, are that important. It's only the numbers that matter. But really, the directions and the words and the way we describe certain numbers, that is all extremely, extremely important in math. So let's pick out that important stuff. We see that we have numbers between 3 and 5. Okay, so between is the key word. Between, that means that it's not actually including 3 and 5. It's only what's in between there. Okay, so go ahead and write not including 3 or 5. Okay, so if you guys remember graphing on a number line, if we don't want to include the numbers that were between, so 3 and 5, we're not including those, we represent that with open dots. Okay, if we did want to include those, we would shade them in. So if we are between 3 and 5, then we are going to shade in between. All right, there's other ways that we can represent this set of numbers though. So another way is what we call interval notation. The symbols, these brackets, as well as parentheses, but the brackets are used to include an endpoint. Okay, so let's underline that. Brackets are used to include an endpoint. So i.e. a closed dot, whereas the symbols, the parentheses, are used to exclude, i.e. an open dot. So in that number line that we did, the set of real numbers between 3 and 5, that means open dot, not included. So we are going to use parentheses. Okay. An interval that extends forever in the positive direction goes to infinity, and then if it's in the negative direction, it's negative infinity. And know that infinity and negative infinity, they're always excluded from an interval, meaning they always receive a parentheses. Not a bracket. And so parentheses, that's an open circle. Why is that? Well, guys, infinity is not a number. It's more like a concept. It just means we go on forever. So if it's not actually a number, how can you include that number? Okay, because it could be any number, really. So always parentheses and open circles for infinity and negative infinity. So let's represent the set of real numbers less than or equal to 7. All right, so first off, if we are less than or equal to, that means we are including 7. We could be equal to it. So first things first, I'm gonna put a closed dot on 7. And if we're less than it, we're gonna shade where the numbers are less than. Okay, and it's just gonna go on forever because it doesn't tell us that we have to be greater than any numbers. It just has to be less than 7 or equal. So for interval notation, we do want to write our numbers as they increasing. So as we look left to right, the numbers should be the smallest on the left, the largest on the right. So we know that our largest number can be 7. We included it. So there's a bracket. And it's going towards negative infinity. And that always will get parentheses. Okay, so make sure you write it in this order because negative infinity is less than 7. Okay, next example. I recommend pause this, try this one on your own. All right, so we're going to represent the set of real numbers greater than -1. So it doesn't say or equal to. So we are not or equal to -1. We're only greater than. So we are going to make an open circle on -1. And if we're greater, then we're going to shade where the numbers are greater. So to the right. Okay, so in interval notation, the smaller number goes on the left-hand side. So -1, we know it's in parentheses because we're not including it. And our number line is going towards infinity. And that gets a parenthesis. All right. The other type of notation that we can use to represent a set is called set builder. So guys, we are just looking and exploring at different ways to represent a set of numbers. Okay, so we have number lines, we have interval notation. Now we're going to talk about set builder notation. Okay, if you see the word set builder, think of fancy brackets. Okay, so interval gets those boring brackets or parentheses. Set builder gets a little fancy. Okay, so it uses the the properties of the elements in the set to define it, okay? We'll also see this symbol here that means an element of. Okay, I'll talk about that more in a second. So this is an example of what you might see for set builder. And so how we read this is the set of all x values. We say x values since there's a blue X written there. Then that line means such that. So the set of all x values such that x is between 3 and 5. Okay, I know it's between 3 and 5 because I do not see or equal to signs underneath my less than symbols. And my numbers I see here are 3 and 5. Okay, and then this guy on the very edge over here, that means that x is an element of all real numbers. Okay, so that capital R is all real numbers. Okay, we don't usually write that. That's implied that these numbers are real. We usually only specify if it has to be a whole number or an integer or something like that. Okay, but if you ever see this on something in the future, especially if you're going to go more into calculus or further up in math, you will see that again. So again, that symbol means is an element of, and that's just a fancy way of saying belongs to. So x belongs to the real numbers. Okay, and oops, I should have, oh, well, I'm not gonna bother writing that again. I just wrote it right there. Okay, so let's now put all these methods we've been working with all together, okay? So in words, let's say we're told numbers less than 3, okay? Well, on a number line, okay, make sure you put your critical number, which is the number you see there, 3. Also, you should put a number less than 3 and a number greater than 3. It's proper to have at least 3 numbers on a number line. So if it's numbers less than 3, it's an open circle because we're not or equal to. Less than means we'd shade to the left. Okay, if we want to write that as an inequality, inequality means these symbols less than, greater than, etc. Well, then we're going to write x is any number less than 3. All right, for set builder, again, think fancy brackets. So I'm going to go ahead and just draw those. Okay, we have, think back to what we just did. We have our set of all x values such that, and then guys, the awesome thing is just write whatever you wrote for your inequality next. So we have our x's such that x has to be less than 3. Okay, so notice that's just what I wrote in the previous box. All right, and then interval notation. I like to kind of look back at my number line to help me out with this one. I know that I'm going towards negative infinity, and I'm also not going above 3. So, and I'm also not including 3, meaning that also gets a parentheses. So parentheses, and we're going from negative infinity to 3. Parentheses around both. All right, next one, we have numbers greater than or equal to -2. So on a number line, if we have -2 as our critical number, do write that on there, and then write a number less than and a number greater than. If we are greater than or equal to 2, that's a closed dot, and greater than means we shade to the right. So in an inequality, we're going to write x is greater than or equal to -2. So for set builder, you're just writing that same inequality, but with that extra fancy stuff. So we have this set of all x's such that x is greater than or equal to -2. And I'm saying it in exactly how it should be read. All right, so then for interval notation, we are not going less than -2. It gets a bracket because it's closed dot and included, and we're just going towards infinity, which always gets a parenthesis. All right, now we have numbers between 2 and 4. Remember, between means we're not including those outer numbers. So on the number line, I put 2 and 4. My third number, I'll just put 3. It really doesn't matter. And I'm going to put open dots on 2 and 4 since they were between, not including, and shade in between. Okay, so that means that x, it must be greater than 2, but less than 4. And we're not saying or equal to. All right, then for set builder, same thing, just put your fancy brackets. So we have this set of all x's such that x is between 2 and 4. And now for interval, our smallest number is 2. We're not including it, so a parenthesis. Our larger number is 4, not including it, so parenthesis. All right, next we have numbers 1 through 3. Through means include, whereas between means don't include. So on the number line, 1 through 3, I'm going to add a third number. We're going to have closed dots. Okay, so then it's going to look very similar to the last example, except now make sure you write your or equal to's. Okay, and so that means these numbers get brackets around them. All right, last but not least, all real numbers. So that's all. How do we do that? Well, I could make up anything, -100, 0, 100, it could be anything. All real numbers, that means we're just gonna shade the entire number line. So for an inequality, we could write that we're going from -infinity to +infinity. Notice I'm not putting or equal to underneath the less than signs, the less than and greater than signs, because infinity, again, not a number, it's a concept, so we can't actually be equal to it. So for set builder, there's really a couple ways you could write this. You could just write it the way we've been doing. You could also write that x, we have our set of all x's such that x is an element of all real numbers. They mean the same thing. And so then for interval notation, we're going to go from -infinity to infinity and beyond. And so we have parentheses again. All right, guys, that is it for classifying numbers. Make sure that you do your practice problems following this video.